In this video, we're going to look at how to analyze and present data in a physics lab report. This should be treated as no more than a guide for students studying physics at the high school level. To start with, we need an experiment to collect data from. I've chosen to look at a trolley rolling down an inclined plane. In particular, I'll be looking at how long it takes for the trolley to roll down different lengths of the inclined plane. From this, I hope to find the acceleration of the trolley. Here's the table of data from my experiment. I chose to have 3 trials for each distance. Hopefully, you've noticed several problems with this table. The headers do not include units, values are stated to different precisions, and no mention is made of uncertainty in the measurements. The table also shows raw data and process data together, which you may or may not wish to separate. For this experiment, I'll make 2 separate tables. This table is a great improvement on the first. I've included the units and uncertainty at the top of the table, though it's equally okay to include these next to individual values. Even though I used a meter stick precise to the nearest millimeter to measure distances, I stated an uncertainty of plus or minus 1 centimeter. This is because I had trouble placing the trolley at a precise distance, and I decided that 1 centimeter was a better measure of the uncertainty. For the time measurement, even though the stopwatch I used measures to the nearest 0.01 seconds, I figured that my measurements were not at all that precise, as my reaction time was a factor. Reaction time for an unexpected event is about 250 milliseconds. So I figured that a fair estimate for the uncertainty in the start and stop of expected events to be about 200 milliseconds. This seems to be a fair estimate, as the greatest difference between time measurements for a given distance is 400 milliseconds, which is equivalent to plus or minus 200 milliseconds. You may have also noticed that I rounded the trial times to 1 decimal place. This was done because the uncertainty is also given to 1 decimal place. This might make you feel uncomfortable, that we're losing information by throwing away the 2nd decimal place. I would argue that the 2nd decimal place was never well known, and if you're unhappy with it, you should redesign your experiment to use a better way to measure time. For instance, by using light gates, which are much more precise. Next, we need to process the data, but we can't do this until we know how to graph the data. To do this, we must first look at the physics of the setup. The equation that describes the motion is given by d equals half at squared. We can rearrange this equation so that the dependent variable is on the left side of the equation. We can now make a straight line graph if we let y equal t squared and x equal d. This yields the following equation. From this, we can see that the slope of the graph is equal to 2 divided by the acceleration, or that the acceleration of the trolley is 2 divided by the slope. This shows that we need to plot the average time squared versus the distance if we are to make a straight line graph. Here we see the results for the average time and the average time squared. Note that there's an additional column for the uncertainty for the average time squared, as the uncertainty is different for each value. Let's look at how the uncertainty was calculated. First, the percent uncertainty in the average time was found. The percent uncertainty in the average time squared is twice this due to the value being squared. Finally, we calculate the absolute uncertainty by multiplying the value by its percent uncertainty. All that's left to do now is graph the data. Here, an XY scatter plot is used. Note that the points are not joined together, but instead a line of best fit has been drawn. The equation for this line is also shown, so that the slope can be used to calculate the acceleration. Using our equation from before, we see that the acceleration of the trolley is 0.5 meters per second squared. To display the error in the graphed quantities, error bars have also been included. The error bars for distance are a constant 0.01 meters wide, whereas the error bars for the average time squared are dependent on the value, which we saw in the process data table. We can continue the analysis by sketching the maximum and minimum acceptable lines of best fit for the error bars shown, but that will be left for another video.